Okay, guys, good morning again. Happy Friday. Lab this afternoon downstairs. Any questions about lab this afternoon? Okay, physical properties, pink sheet. Polarity. Okay, we'll have our first quiz on Monday morning. Okay, over everything we've covered up to now. All right. Polarity. I think we left off right here. Carbonyl is polar. Okay, the CO is a polar bond. Polar bonding arrangement. Carbonyl is very prevalent in many functional groups, and so you just need to be aware of the polarity. And thus the carbon is partial positive, the oxygen is partial negative, because the electrons are being pulled up. The pi electrons are particularly accessible to being polarized. When pi electrons are at a weaker bond, it's easier to polarize it. All right? Even more so than a sigma bond. So this tends to be quite polar. Electrons are moved up to the oxygen. You need to understand what it means by being polar. Okay, there. Other examples, for example, interhalogen. Usually halogens are like ClCl. Let's get interhalogen. Which halogen is electrophilic? The iodine or the chlorine? Not the chlorine. Why do you say chlorine?
Who said chlorine?
It's because the dipole is pointing that way.
It is pointing that way. Why is it pointing that way?
Because of the periodic.
Because what? Chlorine is more electronegative, and so it pulls, right? I'm more electronegative. Okay? So I pull. Pulling the density, electron density away. Okay? Leaving the iodine electrophilic. What does electrophilic mean? Likes electrons. You might say, well, does the chlorine like the electrons? It's electronegative. That's what we call electronegative. It pulls electrons. It likes electrons. Electrophilic means it basically wants electrons. Why does the iodine want electrons? Because the chlorine has pulled them away. And so I'm like, I want electrons. The greedy chlorine left me here wanting electrons. All right? The iodine is electrophilic. That term will become more important. As we go along, make sure you understand what electrophilic means. Partial positive. I mean, that's partial negative. Is a partial negative going to like electrons? No, electrons actually repel. The electrons are going to be more attracted to which halogen? That one. As a result of the chlorine being greedy, that leads to all this. Which one, okay, which one is partial positive, bromine or chlorine? That's the same thing, chlorine here, yeah. Partial positive, partial negative. These are polar. They have a permanent net dipole. They have a dipole moment. Some books will talk about calculating dipole moments based on bond lengths, electronegativity. We're not going to be doing anything like that. Okay. Thus far, just one dipole in the molecule. What about two? O versus H. Oxygen much more electronegative. Difference in electronegativity. All these examples are. Oxygen more electronegative than carbon. Oxygen more electronegative than H, so it pulls. It also pulls here. You've got two dipoles. So what's the net result? Do these dipoles cancel? Have you did vector addition in physics or math? Yeah? Okay, that's what you're doing here. These dipoles cancel?
No.
Are they equal? They are equal. Are they opposite? Exactly opposite? Why not? That's not the right shape. Yes, you got to know the correct shape. What's the correct shape of water? Tetrahedral. And that's 109.5 here. Okay? And so you got two dipoles, these are equal, but they're not opposite. They're going to add up to one dipole, and the one dipole is going to come straight up the gut here. And that's the molecular dipole moment. Direction of the molecular dipole moment. Vector addition. Got to know the correct geometry, right? Yes. What about this guy? Do we have a dipole here? Carbon bromine. Bromine more electronegative than carbon. What about CH? CH is very small difference in electronegativity. So small that we ignore it. A CH bond is considered nonpolar. CH is nonpolar. Just forget about it. The only dipole here you want to consider is that. It's there. There's nothing to cancel that. This is a polar molecule. The more important thing going forward is this carbon is electrophilic. There's partial plus charge here. Partial amount is there. As a result of the bromine being electronegative, it leads to carbon electrophilic or electron poor. There's some examples down here. So water, is water polar or not? Well, we just looked at that. Yes, it's polar. It has a net molecular dipole moment because the dipoles don't cancel. So yes, water is polar. What about CO2? Polar or not? Got to know structure, right? CO2, Lewis structure. Hopefully you can put together a Lewis structure. If you do it, you're going to come up with something like this. Lone pair, lone pair, lone pair. Standard bonding for everything. Is that geometry right? What's the hybridization of the central carbon? SP. Not SP2, SP. How many pi bonds do you see that carbon making? But it's got to have two p orbitals. It's only got two p orbitals if it's SP. SP linear. Two regions, linear. There it is, it's correct. Dipoles. We got what? Here? And here? Are those equal and opposite? Yes, they are, and they just cancel. CO2 is a nonpolar molecule. You can use CO2 as a solvent, cold temperature, liquid CO2, a nonpolar solvent. What are the consequences of that? If you put CO2 in an electric field, would it rotate? Would it experience a torque? Electric field would maybe partial positive up here and partial negative down here. Is it going to turn? Well, this is partial negative, and that's partial negative, that's partial plus. Is that going to turn up here? No, because that would mean that this is turning towards here. It ain't going to do that. It ain't going to respond at all. And we're going to say, this compound looks like it's nonpolar, because it ain't doing anything. Well, we knew that if you knew structure, we knew it wouldn't do anything. All right, there's consequences to this. Because all that was theory, okay? All of it theory until we got to the point where, it's not moving. How do you explain the fact that it's not moving in the electric field? You back up and you look at your theory. Right? Theory tells us it should not move. How about SO2? Okay, I want you to do these on your own. You got to have correct Lewis structure so you can see the individual dipoles if they cancel or not. There you go. Ionics. Well, ionic is, sodium chloride. First off, it never was covalent. But if it was, the chlorine is so much more electronegative that instead of just a dipole, instead of just this, your sodium and chlorine, instead of just this, what happens? The chlorine just rips the arm off and says, okay, I just took all your electrons. I'm so different in electronegativity, and now I have a lone pair, extra lone pair, and now I'm just a formal minus, and left you a plus. It's the extreme of electronegativity. It leads to this. It never was this. It just exists like this. The chlorine just ripped the electrons away when this molecule or this compound was formed. Huge difference in electronegativity. The extreme of polarity. And these are actually formal ions. Ion pair. Pair of ions, right? You know what an ion pair is? Pair of ions. All right? We also call it a salt. Extreme of polarity. Okay, physical properties of various functional groups. Boiling point, melting point first, then we'll look at solubility. Boiling point, to get a compound to boil or to vaporize, the compound must overcome all intermolecular attractions or forces. Intermolecular forces, you should know that term, IMFs, right? Talked about IMFs in Gen Chem. IMFs hold the molecules together, while bonds hold the atoms together of an individual molecule. In general, increased IMFs are going to lead to increased boiling point. Okay? Because to get the compounds to boil, we got to get the molecules to separate from each other. That's when they are able to go into gaseous state. Okay? What types of IMFs are possible? IMFs are also known as stickiness. The molecules sticking together. To what degree? How can they stick together? 4 ways they can stick together. Van der Waals attractions. Now, you may call this London forces or dispersion forces. To me, it's all the same. Okay? These are ranked in order, from weak to strongest. After van der Waals, dipole-dipole, hydrogen bonding, and then ionic. Ionic is the strongest. In polarity, the extreme in polarity, we just mentioned that on the previous page. We'll go through each of these, 1 through 4. 1 first. Van der Waals attractions. Look at this examples here. These 3 hydrocarbons. How do we do nomenclature? Name of this compound. Propane. Pentane. Should be able to name that one too. Look at the difference in boiling points. Negative 4.2. It's a gas at room temperature. Liquid at room temperature. And that was back to a gas at room temperature, with room temperature being about 22 degrees. First 2. Why does this have a higher boiling point? Very good. It has more IMFs. Yes. That's the starting point. But now let's explain that further. What does it have more of? We know it's got more IMFs, because more of my IMFs leads to higher boiling point. But what does it have? Well, we're doing number 1, so you could say it has more van der Waals attractions, and you would also be right, because you know how they outline this laid out. It's more van der Waals attractions, right? Number 1. What does that mean, though? Yeah, it means that too. More energy is needed to get the molecules to separate from each other. Yes? Okay. So let's boil it down to what exactly is going on here and what type of van der Waals. Surface area. Okay. Shown down a little bit, didn't it? What type of polarity does propane have? Have any polarity? No, it's nonpolar. It's just hydrocarbon. CC, nonpolar. CH, we said it's nonpolar. It's all just a nonpolar hydrocarbon. All right? Number 2 is going to be dipole-dipoles. Pluses and minuses like to stick together. All right? This doesn't have any pluses and minuses. But it does. Because pluses and minuses can be sort of temporarily induced, even in a nonpolar molecule. How? By rubbing up against each other. In physics, I think they rub the wall and they make the balloon stick to the wall. Ever do that? They're inducing polarity through mechanical action. Well, everything is electrons. If you rub electrons up against each other, they're going to start moving. And when it moves, it creates some partial positive where the electrons move from. This mechanical action inducing the dipole. What happens when molecules rub together? Around the compound, there's electrons. The electrons bump into each other, and the electrons just get sort of perturbed. And it creates temporary partial plus, partial minus. And that temporary makes it kind of attract to each other a little bit. Very fleeting, very weak. Okay? The molecules are moving. And this weak van der Waals attraction gets created. The main thing here is more surface area you have, the more of this weak temporary dipoles are going to form. And so this has more surface area. Okay? Boom versus boom. More van der Waals attraction, the more energy it takes to get it to boil. What about the compound over there? It's also 5 carbons. 5 carbons and 5 carbons. Same molecular weight. Those two are actually isomers. Why did the boiling point drop?
Branching.
Apparently it has less IMFs. Why? Because it's branching. I'm not sure if is it shown on the right? I think I showed one with a little bit with one more carbon. Branching. When you have branching, you have carbons in the middle that don't add to the van der Waals. Your linear is going to have the most surface area. Branching leads to these things in here, and they can't interact with the neighboring molecules. They're in the middle. Branching leads to less surface area, leads to less van der Waals, leads to lower boiling point. Make sense there? Number 2, which is what? Dipole-dipole. Look at these 3 examples here. Pentane 36. This compound, similar molecular weight, 76. And this one, 78. Why are these two so much higher than that one? Similar size, and thus they're going to have similar van der Waals. Because they have similar surface area. So something else must be going on. What else is going on? These two have permanent dipoles. That one does not. Because they have permanent dipoles and we have partial plus, partial minus, now we have the ability for the partial minus of one molecule to interact with the partial plus of another. And since these are permanent dipoles, this is always there. It's not fleeting and temporary and weak. It's permanent and stronger. And so it leads to more stickiness. Okay? And the molecules start holding hands a little bit. Okay? And to get us to boil, you got to break this handshake here. Put some energy in. Break this interaction. This interaction, by the way, is not a covalent interaction. It's not a covalent bond. What type of interaction is it? It's often called a non-covalent interaction. And we typically indicate that with sort of like this. All right? Non-covalent interaction, the two dipoles, the two opposite charges interacting non-covalently. But you can get all your molecules, right? Everybody in here holding hands. You reach in and do, okay? You can do the same thing for this molecule. No permanent dipole here. All you have there is this fleeting van der Waals, weak dipole stuff. All right? That's called a dipole-dipole interaction. Number 3, hydrogen bonding. Look at these two. This guy 78. This guy 118, substantially higher boiling point. Why?
There's hydrogen bonding.
Thank you. Hydrogen bonding. Now let's explain it. What is hydrogen bonding? Hydrogen bonding is just a special type of dipole-dipole. Special type of number 2. It gets its own name because it's stronger than the average dipole-dipole. Hydrogen bonding is where you have an oxygen N or F lone pair and this will associate with the H that's bonded to an O, N, or F. What's the dipole here? First off, a lone pair, and a lone pair of electrons. The electrons are negative. All right? And we don't often show like partial negative here because that usually is from a dipole. But we just know the electrons are negative. Here you have a dipole, leaving the H partial plus in each case. But these are 3 very electronegative atoms, leaving the H partial pretty strong partial positive. These electrons attracting to the strong partial positive is called a hydrogen bond. Just a special type of dipole-dipole. The hydrogen bond network, it's a non-covalent interaction. We show that. By the way, the oxygen, the thing with the lone pair is called the H bond acceptor. And then the thing that has the H is called the H bond donor. So this shows the acceptor-donor sort of network. Take one molecule of that alcohol. The oxygen can hydrogen bond to the H of another alcohol. While at the same time, the H of this alcohol can be hydrogen bonded to the O of another alcohol. So both the O and the H here are participating in hydrogen bonding. And this non-covalent interaction is particularly strong, stronger than just your average dipole-dipole, like we said. Called hydrogen bonding. Those molecules of that alcohol, it is an alcohol, right? Functional groups. What's the other one? Alkyl chloride, alkyl halide? Yes. The alcohol, we expect the molecules to be more sticky with each other. Previously it was like this. Hydrogen bond is sort of like this. All right? Stronger. Try to break this apart. You're going to need more energy. All right? The one on the right does have dipole-dipole, but it's not as strong as the hydrogen bond, which involves these and only these. H must be on what atom? O, N, or F. Hydrogen bonding. Questions? This guy cannot hydrogen bond to itself. Okay, we already said that. Question. How about this molecule, which is an ether? Can that molecule H bond to itself? Over here we're showing an alcohol hydrogen bonding to itself. By the way, what does it to itself mean? Because I can hold my hand, I'm hydrogen bonding to myself. But what about this? What if he's the same thing? Is this to the self?
Yeah.
We need to explain that. This is 2 different molecules interacting. We call that intermolecular. So that's an intermolecular hydrogen bonding network that I'm illustrating, right? Different molecules. We could have internal. I think I showed that later. Intramolecular. Can this hydrogen bond to itself? What I mean here is, can a hydrogen bond to another molecule of the same? No. What do you have to hydrogen bond? You have to have an acceptor and a donor. This is just like Velcro. You got two pieces of Velcro. One of them is fuzzy, one of them is more loopy. What if you have two loopy pieces of Velcro? They don't stick together, right? Hydrogen bond requires an acceptor and a donor. All right. Could you show a hydrogen bond network with this? I only see an acceptor. That compound has no donor. Cannot hydrogen bond to itself. Question though, can this molecule hydrogen bond to water?
Yes.
Yes, it can hydrogen bond to water. You could show water here, and you can show the oxygen as a hydrogen bond acceptor and the H of water being your hydrogen bond donor. So it can interact with water. That's important when you start talking about things like solubility or interaction with solvents. Okay? Because to dissolve in a solvent, it's got to want to associate with it and like it. Okay? Your IMFs are the ways that molecules can interact with each other. If there's no IMF, that means there's no interaction, and they're not going to like each other. Question down here. How many H bond acceptors and donors does effexor have? How many donors? One, yes, right here. H is on an O, N, or F. By the way, since we always show the H when it's on an O, N, or F, because we only do not show it when it's on carbon, your hydrogen bond donors are always going to be shown in as H's. How many acceptors in this molecule? 3. Anybody say another number other than 3? Everybody say 5? I mean, there's 2 lone pairs here. Could each one hydrogen bond? It's possible. Yeah. I would ask for that to be clarified. How many acceptors? I would say, are you saying acceptor atoms or acceptor lone pairs? If we say acceptor atoms, it's 3. All right. Let's look at these examples here. These 2 are constitutional isomers, same formula. They're isomers. Why does this one have such a higher boiling point? Hydrogen bonding. These molecules can hydrogen bond to each other. You can envision that? Can these molecules H bond to each other? No. These are constitutional isomers. Why does this one have such a higher boiling point? Hydrogen bonding possible between the molecules. Water. Why has water got such a higher boiling point than H2S? H2S is 160 degrees lower boiling point. Why? Hydrogen bonding. Can H2S hydrogen bond to itself? No. Below, this is butane. This is antifreeze. We would just replace each carbon on the end with an oxygen. Very similar molecular weight, very similar surface area. Why does this one have a boiling point that's 200 degrees higher? Hydrogen bonding. Hydrogen bonding is often the answer to lots of things as we move forward and as you get into biochemistry. What holds DNA together? Hold on. Thank you. All right. Why does AT go together and CG go together? Hold on. Okay, the fourth. Ionic. Ionic is the strongest. Because here you don't just have partial charges. You know, you have Permanent partial charges. Now we got permanent formal charges, full charges. Ionic. Strongest attraction because you got a full ion and a full cation, a full anion, strong attraction. More than just partial charge. Going to be strongest. In ionic compounds, for example, this alcohol is 1.78. If we convert it to the salt here, that can be done and make the oxygen an anion and have some type of counter-cation here. This has a boiling point greater than 500 degrees. Because now in the mass of your compound here, you got all these ions just like concrete to each other. All right? Very hard to get those to separate. Permanent, full, formal charges. And of course, something with such a high boiling point is probably also going to have a high melting point, and ultimately it's going to make salts tend to be solids at room temperature. 99% of your salts are solids, right? Because they have such strong IMFs, they're just stuck and they have no mobility and it's just solid. Liquids, the molecules have to move a little bit. Okay? Okay? Move a little bit in liquid. Solid is like so strong. We're like, okay, we're fixed. We're like this, solid. Liquid, less IMFs. We can get a little flowing. Okay? 2 molecules. Gas. Down, gas. All right? Strong IMFs, solid, high boiling point, high melting point. Let's look at melting point. Same arguments throughout. IMFs must be weakened to go from solid to liquid, right? Which would have a higher melting point? One is 126, one's 44. Which one of these is 126? This one's 126, this one is 44. Why is the melting point higher? More IMFs. Okay, let's get beyond that. Why does this have more IMFs? Hydrogen bonding, because look, these are H's here on a nitrogen. Right? Let's show it bonded out. We can have another molecule, aromatic, sometimes AR. Okay, H2. We can show hydrogen bonding right here. Oxygen lone pair as a hydrogen bond acceptor, H on a nitrogen, H bond donor. These molecules are going to be holding hands a good bit by a strong H bond. Can these molecules hold hands by H bond? No, I see acceptors. By the way, I don't think that's a good acceptor. Why not? What type of orbital is this lone pair in? P orbital. It's busy doing resonance. It's localized. Probably not a great hydrogen bond acceptor.
So that same would go for the molecule that can hydrogen bond. Would it not be a good acceptor?
Yeah, that's perhaps why I didn't use that as an acceptor. I used that lone pair as an acceptor. Because those lone pairs are not in P orbitals. It's up to debate. Can that hydrogen bond? I wouldn't ask you to decide, but what I would want you to know is that it may not hydrogen bond as good as some other one. This cannot hydrogen bond to itself. It's like asking 2 pieces of the sticky Velcro to stick together. No, you need 2 different types of Velcro. Sticky and fuzzy. Or loopy and fuzzy. Okay? Hydrogen bonding. You have to be able to recognize it and the consequences of it. All right? Melting point is the same considerations as boiling point. Basically evaluating your IMFs. Okay, solubility. Important. Like dissolves like. A compound will dissolve best in a solvent that has similar IMFs. So they can be very friendly and they can interact with each other by those IMFs. Okay? Types of solvents. First off, broad classification. You got water and you got organic solvents. In Gen Chem, they tell you water is a universal solvent. Is that right? Well, they lied to you. Water is a terrible solvent. It's good for salts, ionics, because ionics are very polar and water is very polar. All right? But there's many more compounds than are salts in organics. There's way more organic compounds than inorganics. All right? In general, an organic compound is going to form an organic solvent, not water. Let's look at organic solvents. I classify these as two different types, polar versus nonpolar. All right? Polar ones I show over here. You got to be careful though, because diethyl ether is actually a polar molecule. So why am I showing it as nonpolar? Because this means to me, and to most chemists, this is water soluble. Polar solvents are water soluble. That's how I'm calling it. If it ain't soluble in water, I classify it as nonpolar. And diethyl ether, even though it's a polar molecule, is not soluble in water. None of those over there are. These are useful for extractions, where you want to have two layers, a water layer and then an organic solvent layer. You cannot use those over there for extractions because they just mix with water and you only have one phase. Why is diethyl ether not soluble in water? It's a polar molecule. Water is very polar. Problem is, it also has lots of hydrocarbon, and hydrocarbon is nonpolar. And it's the hydrocarbon part that sort of keeps it from not wanting to mix with water. Okay? Same thing with, well, that's the answer there. See, these over here are polar, but they also have only a small amount of hydrocarbon. Too much hydrocarbon and it ruins any polarity that you might have. You don't need to memorize these, but you need to refer back to this often. And as you go along in Organic 1, Organic 2, you need to become familiar with your solvents. Okay? This is a reference page here. Understand the general ideas of how I group them. All right? And then maybe somebody says, what do you mean diethyl ether is not polar? Surely it is. It's got two dipoles that don't cancel. Then you can explain to them why you're calling it nonpolar. Question?
Are these the most common solvents?
Yes, I'm showing you some of the most common solvents. Yes. Exactly. Question?
So would we have to predict on the test if a molecule is or soluble or not soluble in water?
That can be difficult. If you do an absolute prediction, difficult. Relative, you should be able to do that. For example, if I took one of these carbons off, here, I'll do this for you. Acetone, soluble in water. Okay? If you add one more carbon, guess what? It ain't. As a student, you're not going to know that cutoff. But does it make sense that one more carbon will make it up when you compare the two? Relative comparisons are easier than absolute answers. Okay? It's amazing. One more carbon and it will no longer mix and you end up with two phases. Alcohols. Lots of hydrogen bonding with water. Okay? But look. I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8. Octanol. It's an alcohol. But it ain't soluble in water. Because there's too much hydrocarbon. And octanol is often used for in a certain case. That's why I just point that out. We'll probably not see that case, but it's not. It's too much hydrocarbon. Okay. Water. What's it good for?
Organic salts.
I thought you were going to say
Hydrogen bond.
absolutely nothing. It is good for salts. sodium chloride, potassium phosphate, lithium sulfate, those are salts, right? Potassium bromide, okay? Water's good for those because water's highly polar. Water's your most polar solid. Until we talk about exceptions, unique thing. Salts are your most polar compounds. They like each other. Like dissolves like. Okay? Will organics dissolve in water? Any organics? In general, no. But do some dissolve in water? You ever dissolve sugar in water at home? Usually you have to warm the water. But it will dissolve, and then it'll stay dissolved when it's cooling. Sugar's a neutral organic molecule. But it's got lots of OH groups, which gives it lots of hydrogen bonding. Yes, highly polar organics will dissolve in water. How about salts? Do all salts dissolve in water? In general, yes, but there are exceptions. A couple of notable exceptions. Calcium oxalate. It's actually an organic dianion. Okay? Calcium oxalate. Not soluble in water, even though it's a salt. Because of that, it causes problems in the body. It forms kidney stones. Get too much of it, it starts forming solids, precipitating. It crystallizes out because the solubility is low in your kidneys. By the way, what solvent is in your kidneys? What's around there? Water or acetone? Water. You might think the calcium oxalate would be soluble in water. It's got very low solubility, even for a salt. Okay? What about this guy? It's ionic, soluble in water. Actually not that soluble. By the way, it's got lots of organic. But it's also very polar. So why is it not soluble in water? Well, that's a deeper discussion. But it's not, and it causes gout, because it forms solid in your joints. And the water just can't dissolve it. And the solid causes problems. So there's a couple of sort of medical-related salts that are not soluble in water and thus cause problems. Organic solvents, okay, you can read the rest. We basically already alluded to it. Question. Which carboxamide on the previous page will be most soluble in hexane? Here are two carboxamides or amides. Which one would be more soluble in hexane? Hexanes. Right. Keep in mind, we're going to start with a solid, and we're going to say, okay, we want you to dissolve in hexane. Hey, molecules, we want you to all break apart and go associate with hexane instead. Are these going to want to break apart and go associate with hexane? No, these are nicely hydrogen bonded together. And these are not held together as much. And so they're more willing to break apart and go interact with hexane. All right? Because to dissolve something, you also have to break the IMFs. And hopefully create new IMFs with the solvent. Okay, there's some extraction down there. We'll come back to that. Basically, be looking at extraction. Please be looking at extraction. Very important to understand the principles of that. It also includes acid-base chemistry. And so I'm going to wait until we cover the acid-base on the next handout before we really get into extraction. All right? IMFs. Well, this is how drugs bind to drug receptors. What is this? Crestor? You ever heard of Crestor? Have you ever watched TV? This is Crestor molecule, beautiful organic molecule, sitting in the enzyme pocket, binds to an enzyme, probably called HMGA-CoA reductase. It inhibits that enzyme to keep your body from producing so much cholesterol. How does it interact with the enzyme? Well, how does any molecule interact with any other molecule? By IMFs. What type of IMFs are possible? 1 through 4. It shows different IMFs. Got to be very careful because sometimes non-chemists are drawing things out there. Let's look at this. What are they trying to show here? Yeah, I mean, I would probably want to show your lone pairs here. They're showing this condensed. This is reasonable hydrogen bond. But what about this here? What in the world is this? Is this an H, hydrogen bonding with an H? That don't make sense. Okay, you got to be careful with some of this. This should be what? This should be the lone pair interacting over here with that H. You see? You should see what's wrong with this here.
Yeah. Are they showing a hydrogen bond between leucine and alanine to that, yes, that's
No.
not a, that,
No, because the CH doesn't
Yeah,
hydrogen bond,
that's-
only OH and HFH.
yes.
What is this? These are amino acids. You know your amino acids? What type of side chains do these have? Hydrophobic, hydrocarbon. Hydrocarbon side chains. How is a hydrocarbon going to interact with a hydrocarbon? Somebody said something. Louder. Van der Waals, right? First example we showed two propane molecules interacting, hydrocarbons interacting by van der Waals. That is an interaction. It's weak, but it is something. Yeah. This hydrocarbon is interacting with the hydrocarbon of these amino acids by van der Waals. They're calling it hydrophobic bonds. First off, that's very hydrophobic. That ain't going to like water. So that's where that comes from. And also, it's not a true covalent bond. This is a non-covalent interaction. But a hydrogen bond is also a non-covalent interaction. We still call that a bond. Yeah, I would call this some van der Waals attraction. You got to know what amino acids here. Coming off of leucine is like an isobutyl. Can these two groups interact in any way? Yeah, by van der Waals. Not by dipole-dipole, not by hydrogen bonding. Yes, something like this, I can't discuss every little detail. You have to look at it and ask questions. There's your learning opportunity. Okay? The main thing here is, how does a drug interact with the enzyme? They're IMFs. And be careful with what's out there. So somebody doesn't know how to show a hydrogen bond. What type of interaction is this here? You could call that hydrogen bonding because this is an O lone pair and an H, but it's also an ion and an ion interacting. So that's also could be called a ion. What do I call it for? Ion or ionic interaction, right? Because they're both ions. Okay. Below. So, when you took a bath this morning or last week, what did you use? Water? But you're usually washing off the oils from your hair. Oils are not soluble in water. So that's why you use soap. Because a soap is like a mediator. A soap has polar parts to like the water, and it has hydrophobic parts to like the oils, and it brings them together. Soaps often exist like this, micelles. The polar part is on the outside, and it can interact with the water, and then the grease gets trapped in the middle, and it interacts with the hydrophobic part of the soap. So understanding the anatomy of a soap. Okay, here's a soap. Usually fatty acid. Got this acid anion head group, and then fatty. Hydrophobic. Fatty is a slang term for hydrocarbon, hydrophobic. This interacts with water, this interacts with the oils, and everything goes down the drain. Have a good weekend, guys. See some of you this afternoon.